All right, this is the last FRQ question for the second practice test. Matthew is interested in purchasing a digital camera and notices that as each model's image quality in megapixels increases, the cost appears to increase linearly. A scatter plot and regression output of the megapixels versus costs for 7 randomly chosen camera models is below. All right, part A. Using the regression output, write the equation of the fitted regression line in context. Okay, so let's first write the formula. Okay, so in statistics, we write y hat equals a plus bx, okay, where a is the constant or the y-intercept, right, which is this value right here. That's a. B is the slope of the regression line, which is that value there, right? So you can kind of see how, like, here's the line, right? It would be, its intercept would be somewhere right around 70, so this number makes sense. And then the slope is positive. I don't know, it looks like for 4 megapixels, it increases by $50. So like 50 divided by 4 would be like 12.5-ish, and that number is kind of in the ballpark. Okay, anyways, let's just write y hat equals 63.457 plus 16.2809 times x. However, that is not in context, so we're going to replace the letters x and y with megapixels and cost. Okay, so predicted, and then I write y. Silly me. All right, predicted cost equals $63.457 plus an additional $16.2809 per megapixel. Okay, there we go. Part B, interpret the slope and y-intercept in the context of the problem. All right, so slope is the change in y versus the change in x, or in this case, it's really the change in y hat. Okay, so we could say for every additional megapixel, the predicted cost will go up by $16.28. Okay. For each additional megapixel, the predicted cost of the camera increases by $16.2809. 28 cents. Okay. The y-intercept is the point of our regression model where the x value is 0. Okay, so when a camera has no megapixels, the model still will predict its cost, even though, you know, what is a camera if it doesn't have any megapixels? That doesn't make any real world sense, but we can still write the interpretation. Right. For a camera with 0 megapixels, the predicted cost is $63.45-ish. Let's put the dollar sign there for the units. All right, clearly this problem is pretty dated. I don't think you can get a digital camera that cheap anymore, but that is beside the fact. Okay, part C, construct and interpret a 98% confidence interval for the slope. Assume the conditions for inference have been met. Okay, so this is our 4-step problem. All right, we're going to choose the procedure. This is a t interval for slope. Confidence level 98%. All right, the parameter beta is the true slope of the population least squares regression line relating megapixels to cost. All right, and I think that's it, right? We're doing an interval, so no need to write any hypotheses. I'll probably put the statistic. The statistic is 162809. All right, let me just move that, create a little bit more space for myself. Right, for the next step, it says assume that it's met. Assume met. Okay, so then we can go on to the calculation step. All right, general formula, point estimate plus or minus margin of error. Specific formula, right? B is our statistic, plus or minus T star is our critical value, and then SEB represents the standard error. Okay, so our statistic is 162809. Plus or minus, okay, our critical value. So we've got 98%, and it was 7 cameras. So degrees of freedom, let me just write it here. N minus 2, 7 minus 2 is 5. Okay, so 5 degrees of freedom, 98% confidence. Is right there. So 365. 3.365 times the standard error is that number right there, SEB, 8192. Okay. All right. I'm doing this off screen. I'm going to calculate the endpoints of this interval. 162809 minus 3.365 times 0.8192. Okay, so the left endpoint is 1352, and the right endpoint is 1904. Okay, and now we just need to write a conclusion. We are 98% confident that the interval from 1352 to 1904 captures the true slope of the population least squares regression line relating megapixels to cost. Okay, so that's kind of like the generic interpretation. What this really means is that for the population of all cameras, we expect that for every extra megapixel, it's going to raise the cost by $13.52 to perhaps as much as $19.04, right? So somewhere within that range is basically the cost per megapixel for the population of all cameras.